You're the one introducing us.
Hello, I'm Raven. We're 2056, and
I'm AJ.
I'm Isaac Zinda. I'm a sophomore at SAS, and I'm taking advanced math this year.
I'm Matt.
I'm Alec.
I'm Nate.
And I'm Spencer.
so we wanted to be a successful team this year, and so we decided to build a game strategy to encase that goal of being a successful team. How did we find a good game strategy that would propel us to become a successful team? We started out by making board games with rules that were similar to the game from this year. We learned that the robots that were doing consistently well in the endgame and the autonomous were doing better than the robots that were picking up blocks in teleop. You're making more points with putting a block in the pendulum during the autonomous, hanging or raising the flag in the endgame than you are picking up a few blocks during the teleop. Think of football. You don't make points off of the field goals after a touchdown. You make points on the touchdown.
So, in order to better execute our game strategy this year, we decided to create our entire robot in CAD, or computer-aided design. So, this is a computer model of our chassis, and this is a computer model of our arm, both of which we built as we built the physical counterparts. And so CAD allowed us to do a couple of cool things. For example, it allowed us to print these ball bearings and to print more quickly. And it also allowed us to run computer simulations of how we were going to integrate the different systems. For example, we had trouble figuring out how we were going to make the arm fit within the 18 cubed box. But with CAD, we were able to put it into this model and figure out which was the best and most efficient use of space.
CAD and rapid prototyping were very important for the hanging and the autonomous. CAD allowed us to design a very good interface between the robot and the arm, which allowed for massive structural integrity, as is needed to hang a 25-pound robot with two pretty small motors. A very high gear ratio was needed, all of which was mapped out in CAD beforehand. Prototyping also allowed us to create a very effective block dispenser for using in the autonomous. We began with this very simple block dispenser, just a piece of wood, but we could get very many prototypes in fast, many different angles, many different ideas. We finally settled on this design you see now. Then, we competed in our first game. By that time, we buffed it up and created it with metal, but we soon realized that it would not be as effective because the front was very delicate and vulnerable. So, we progressed to our third iteration. Using the bar you see here and these supports, allow it to run at full speed into almost any wall, almost 10 miles per hour, and not suffer any hits. We've tested this many times. The combination of the integrity of our arm, which was helped with CAD, and the efficiency of our block dispenser, which was helped with prototyping, allowed us to compete more effectively in the autonomous and hanging periods of the game.
Our working with the community had a huge influence on both our robot design as well as game strategy.
We were sponsors Synapse, who taught us to keep things organized and keep things simple so that we could be more effective. And we held a workshop actually, at which we helped young teams, but we also learned a lot ourselves. And we actually learned about it for our game strategy and for our
But there's more than just learning from the community. We also want to be able to give back. So during the summer, we hosted a summer camp for all the members of the team that you see here and some other members of the school, where you could get influenced and have ideas taught by other mentors about robotics. There's also a middle school club that's working with FLL. AJ helps with that, and he gets all these little minds, excited and lit up about programming and physical components. And Madeline was doing the same thing, trying to inspire girls to get more interested in science and technology. So she made a video relating makeup and creating a robot. I'm switching. I'll switch quickly. Driving practice was a big part of our game strategy. We wanted to be able to have effective driving because there's a lot going on in the field. Something more about driving practice, yada, 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 yada. Autonomous was also a big part. And autonomous, we wanted to be able to get on the ramp, but also get points to the blocks. We were trying to get the highest scoring value, but also be the most efficient at it. That meant that we had to be fast fast and get there before the robots, but also be accurate.
So this year, in order to further enhance our game strategy, we use a program called I2C, which bypasses robot C and goes straight from the NXT to the motor controller and then to the motor, which means that we get a lot more precision and it adapts in a dynamic situation, and it isn't affected by field obstacles as much. And if the robot is slowing down, like with normal robot C, you send it motor power, the motor stays at that power, and even if it goes over an obstacle, it will slow down. But with I2C, the motor detects that and it will speed up, so you maintain a consistent speed, which means that our autonomous is consistent on every field that we go to. Another thing about our autonomous is that that grid of 9 on the ramp means that we can get to any one of those 9 spots by entering an option on the NXT when we start up the autonomous.
Another way that we improved our game strategy is by improving how fast we did prototyping and how we tested those prototypes. So we made a program called EasyC, and EasyC is really an easy way on your web browser to make robot C code to drive robotic parts and prototypes. And so all you have to do is type in values like move motor or whatnot, and then that will spit out all this text that you put into your right into robot C, and then upload it to your NXT, and you're done. And so that was kind of like a nice way that we were able to keep our pace going as we were